In mathematics, the Langlands program is a web of far-reaching and influential conjectures that relate Galois groups in algebraic number theory to automorphic forms, and representation theory of algebraic groups over local fields and adeles. It was proposed by Robert Langlands. Background. In a very broad context, the program built on existing ideas. The philosophy of cusp forms formulated a few years earlier by Harishchandra and Gelfand, the work and approach of Harishchandra on semi-simple Lie groups, and in technical terms the trace formula of Selberg and others. What initially was very new in Langlands' work, besides technical depth, was the proposed direct connection to number theory, together with the rich organizational structure hypothesized. For example, in the work of Harishchandra one finds the principle that what can be done for one semi-simple Lie group, should be done for all. Therefore once the role of some low-dimensional Lie groups such as GL in the theory of modular forms had been recognized, and with hindsight GL in class field theory, the way was open at least to speculation about GL for general n greater than 2. The cusp form idea came out of the cusps on modular curves but also had a meaning visible in spectral theory as discrete spectrum, contrasted with the continuous spectrum from Eisenstein series. It becomes much more technical for bigger Lie groups, because the parabolic subgroups are more numerous. In all these approaches there was no shortage of technical methods, often inductive in nature and based on Levi decompositions amongst other matters. But the field was and is very demanding, and on the side of modular forms, there were examples such as Hilbert modular forms, Siegel modular forms, and theta series objects. There are a number of related Langlands conjectures. There are many different groups over many different fields for which they can be stated, and for each field there are several different versions of the conjectures. Some versions of the Langlands conjectures are vague, or depend on objects such as the Langlands groups, whose existence is unproven, or on the L group that has several inequivalent definitions. Moreover, the Langlands conjectures have evolved since Langlands first stated them in 1967. There are different types of objects for which the Langlands conjectures can be stated. Representations of reductive groups over local fields. Automorphic forms on reductive groups over global fields. Finite fields. Langlands did not originally consider this case, but his conjectures have analogues for it. More general fields, such as function fields over the complex numbers. Conjectures. There are several different ways of stating Langlands conjectures, which are closely related but not obviously equivalent. Reciprocity. The starting point of the program may be seen as Emil Artin's reciprocity law, which generalizes quadratic reciprocity. The Artin reciprocity law applies to a Galois extension of algebraic number fields whose Galois group is abelian, assigns L functions to the one-dimensional representations of this Galois group, and states that these L functions are identical to certain Dirichlet L series or more general series constructed from Heck characters. The precise correspondence between these different kinds of L functions constitutes Artin's reciprocity law. For non-abelian Galois groups and higher dimensional representations of them, one can still define L functions in a natural way. Artin L functions. The insight of Langlands was to find the proper generalization of Dirichlet L functions, which would allow the formulation of Artin's statement in this more general setting. Automorphic forms. Heck had earlier related Dirichlet L functions with automorphic forms. Langlands then generalized these to automorphic cuspidal representations, which are certain infinite-dimensional irreducible representations of the general linear group GL over the adel ring of Q. Langlands attached automorphic L functions to these automorphic representations, and conjectured that every Artin L function arising from a finite-dimensional representation of the Galois group of a number field is equal to 1, arising from an automorphic cuspidal representation. This is known as his reciprocity conjecture. Roughly speaking, the reciprocity conjecture gives a correspondence between automorphic representations of a reductive group and homomorphisms from a Langlands group to an L group. There are numerous variations of this, in part because the definitions of Langlands group and L group are not fixed. Over local fields, this is expected to give the parameterization of L packets of admissible irreducible representations of a reductive group over the local field. For example, over the real numbers. This correspondence is the Langlands classification of representations of real reductive groups. Over global fields, it should give a parameterization of automorphic forms. Functoriality. The Functoriality conjecture states that a suitable homomorphism of L groups is expected to give a correspondence between automorphic forms or representations. Roughly speaking, the Langlands reciprocity conjecture is the special case of the Functoriality conjecture when one of the reductive groups is trivial. Generalized Functoriality. Langlands generalized the idea of Functoriality. Instead of using the general linear group GL, other connected reductive groups can be used. Furthermore, given such a group G, Langlands constructs the Langlands dual group LG, and then, for every automorphic cuspidal representation of G and every finite-dimensional representation of LG, he defines an L function. One of his conjectures states that these L functions satisfy a certain functional equation generalizing those of other known L functions. He then goes on to formulate a very general Functoriality principle. Given two reductive groups and a morphism between their corresponding L groups, this conjecture relates their automorphic representations in a way that is compatible with their L functions. This Functoriality conjecture implies all the other conjectures presented so far. It is of the nature of an induced representation construction, what in the more traditional theory of automorphic forms had been called the lifting, known in special cases, and so is covariant. Attempts to specify a direct construction have only produced some conditional results. All these conjectures can be formulated for more general fields in place of Q, algebraic number fields, local fields, and function fields where P is a prime and A is the field of rational functions over the finite field with P elements. Geometric conjectures. The so-called geometric Langlands program, suggested by Gerhard Laumann, following ideas of Vladimir Drinfeld, arises from a geometric reformulation of the usual Langlands program that attempts to relate more than just irreducible representations. In simple cases, it relates L-adic representations of the L fundamental group of an algebraic curve to objects of the derived category of L-adic sheaves on the moduli stack of vector bundles over the curve. Current status. The Langlands conjectures for GL follow from class field theory. Langlands proved the Langlands conjectures for groups over the Archimedean local fields R and C by giving the Langlands classification of their irreducible representations. Lustig's classification of the irreducible representations of groups of Lie type over finite fields can be considered an analog of the Langlands conjectures for finite fields. Andrew Wiles' proof of modularity of semi-stable elliptic curves over rationals can be viewed as an instance of the Langlands reciprocity conjecture, since the main idea is to relate the Galois representations arising from elliptic curves to modular forms. Although Wiles' results have been substantially generalized, in many different directions, the full Langlands conjecture for GL remains unproved. Laurent Laforgue proved Laforgue's theorem verifying the Langlands conjectures for the general linear group GL for function fields K. This work continued earlier investigations by Drinfeld, who proved the case GL local Langlands conjectures. Philip Kutzko proved the local Langlands conjectures for the general linear group GL over local fields. Gerhard Laumann, Michael Rapoport, and Ulrich-Stuhler proved the local Langlands conjectures for the general linear group GL for positive characteristic local fields K. The proof uses a global argument. Richard Taylor and Michael Harris proved the local Langlands conjectures for the general linear group GL for characteristic zero local fields K. Guy Henniot gave another proof. Both proofs use a global argument. Peter Scholzer gave another proof. Fundamental lemma in 2008. Gobaut-Chow proved an auxiliary but difficult statement, the so-called fundamental lemma, originally conjectured by Langlands in 1983.